Hey everyone, welcome to the third video for section 3.7. So in this video we're going to let the damping coefficient be non-zero and see what happens. And it turns out in that case there are a lot of different things that could possibly happen. So we're going to look at all of them, see what all the different cases are, and then for this video we're just going to look at the first of the cases where the damping coefficient is smaller than some certain value that we'll talk about in a little bit. So if that happens, you still get oscillation, but they're a little bit different than before, and we'll see exactly how they're different and how it all comes together. So let's go ahead and get on into it. So in this video, we're looking at now damped vibration. And by that I mean we're back to our entire equation from before, except we're still assuming that it's unforced, so our right-hand side is still 0. So we have an mu double prime plus a gamma u prime plus a ku equals 0, and we can just try to solve this right away. So we get a characteristic equation, mr squared plus gamma r plus k equals 0, and then we can use the quadratic formula to find our roots. So then our roots here are r equals negative gamma plus or minus the square root of gamma squared minus 4km all over 2m. And this is, if you want to factor this out, a gamma over 2m negative 1 plus or minus the square root of 1 minus 4km over gamma squared. Either case, that gives you the roots of this equation. So we see, as before, there are going to be three cases based on what the sign of gamma squared minus 4km is, whether if it's negative, positive, or 0. Again, since all of our constants are positive here, we get just monotone and all these things because everything's going to be positive. So there are three cases here. We have case 1, where gamma squared minus 4km is positive. What does our solution look like there? Well, in this case, we're going to have two roots that are going to be real and distinct. So we're going to get our solution is going to be something like a e to the r1t plus b e to the r2t. And you can find those constants r1 and r2. They're just solved from the equation up here, but they're going to be two real and distinct roots, so we're going to get something like that. In case 2, we'll have gamma squared minus 4km equals 0. And this is going to be our repeated root case where we're going to have our t e to the t term show up. And so our function u of t is going to look like a e to the negative gamma t over 2m, because we know what our root is. It's gamma over 2m times t plus b t e to the negative gamma t over 2m. And finally, we have probably the most interesting case of the three, the last one, when you have gamma squared minus 4km less than 0. This is when we're going to get oscillation. So our u of t is going to be, because this gives us imaginary numbers, e to the negative gamma t over 2m, that's still our real part, times a cosine of mu t plus b sine of mu t, where I'll write out what that mu is. This mu is given by the square root of 4km minus gamma squared over 2m. That just comes from flipping the minus sign from before, so I get the square root of a positive number instead of the negative number to give me the i's. So these are our three cases here for what could happen. Now the main thing to notice from all of this is that all of my constants are positive in this problem. So I know that if I look at the numerator, so I have minus gamma plus or minus the square root of gamma squared minus 4km. I know that gamma squared minus 4km is going to be strictly less than gamma squared, because if k and m are both 0, the problem's not interesting at all. So we're strictly less than gamma squared, which means this guy always has negative real part. Because if the square root part is imaginary, then our real part is just negative gamma over 2m, which is negative. If the middle part is 0, we're again negative gamma, which is still negative. And if this part's going to be positive on the inside, it's still going to be in magnitude less than gamma, which means since I'm starting at negative gamma and I'm adding something smaller than it or subtracting something smaller than it, I can't get back to 0. So this is always going to have negative real part, which means all these solutions above all go to 0 as time goes to infinity. Because all of them, I'm going to scroll back up for this, all of them have an exponential term that's going to have a negative power on it. So this will be negative, this will be negative, this is negative, this is negative, and this is negative. which means as time goes to infinity, these things are all going to 0 because e to the t goes to 0 faster than t goes to infinity. So everything's going to 0 as time goes to infinity, which is going to be important when we get to section 3.8 and talk about forced vibrations. These are going to be what are called transient solutions because they go away as time goes on. Now each of these three cases have names, so I'm going to write them down so you have them. This case here, the first case, is what's called an overdamped solution. The second is called critically damped, and the third is called underdamped. So in this video, what we're going to look at is just the underdamped case. We'll hit over and critically damped in the next video, but for this one, we're just going to go back and look at the underdamped one a little more specifically. So as we saw before, in this case, we're going to get oscillations again. And if we had the same setup as before, we know we can reform this to get in terms of r cosine of mu t minus delta, because we had our solution looked like this, which I can transform to look like an e to the minus gamma t over 2m r cosine of mu t minus delta in the same way we did before. There's nothing new happening here, so I'm not going to explain it again. This is what we call a damped oscillation. This mu, which we had the formula for it before, but I'll write it again, is called the quasi frequency because the function's almost a periodic oscillation, right? It's a periodic oscillation, but it decays over time. So we can't call it an actual frequency because it's not quite the right thing, but it's almost a frequency. So that's called the quasi frequency. And to get an idea of what's going on, let's compare this to the frequency for undamped motion. So what I want to do is I want to look at mu and divide it by my undamped frequency, omega 0. And if we work all this out, this becomes 1 minus gamma squared over 4km to the 1/2. So it's slightly less than the frequency from the original case, right? Our new frequency is this times something 1 minus something positive, so it's going to be slightly less than our original frequency. So it's going to slow down a little bit in the oscillation, but not too much, especially if gamma is small. And really, when you're talking about underdamped system, you're talking about small damping coefficient gamma. So this is for small gamma. Because as gamma gets larger and larger, this ratio here is getting closer and closer to 1. And when that gets to 1, we have other problems. Namely, we get into the critical damped and overdamped cases. So we have our quasi frequency, which ends up being slightly less than our original frequency, and we'll see pictures of this in the next video. We also then have our quasi period, which I bet you can guess what that is. That's just 2 pi over mu, which is then going to be slightly longer than our original period for the same reasons, because if the frequency is a little bit bigger, the period gets smaller. So this period is a little bit longer than we had for our other one, because we have a smaller frequency. And the important thing we see showing up, which is going to come up again and again, is this ratio right here. The ratio gamma squared over km ends up being an important factor in a lot of this stuff. It's an important factor in all of these calculations. Really what it does is it indicates how much the dampening affects the rest of these, how much the damping affects frequency, how much the damping affects the problem as a whole. Because if gamma is 0, this is 0, and so it has no effect in the system because there is no damping. As gamma gets bigger and bigger, you'll see this ratio showing up in how the damping really affects the system and how it changes things about the system and how it behaves. All right, so that's it for this video. The next one, we're going to talk about critically and overdamped solutions and how they behave differently than this one. And we'll show some Maple code to show how these all work and what they all look like. All right, thanks for watching, and I'll see you in the next one.